Welcome to 5.4 Logarithmic Functions. To begin, our objectives are to change exponential statements to logarithmic statements and change logarithmic statements to exponential statements. We're kind of going back and forth, that way we get comfortable with anything that we see, we can change to one or the other. Evaluate logarithmic expressions, determine the domain of a logarithmic function, graph our logarithmic functions, and solve logarithmic equations. So it's a jam-packed logarithmic day. To begin, let's take a look at what a logarithmic function is. When we look at the relationship between logarithms and exponents, we can see that they are inverses, actually. If we take the base from our exponential and put it into our logarithmic form, it continues to be the base. So over here, we would read this log as log base a of x is y. That's how we would read this. And the base of our exponential form is the base of our logarithmic form. The exponent from our exponential form is what our log equals. And then we can see that what our exponential equals is inside of our logarithmic function. Here's an example. Turning log base 2 of 8 equals 3 into exponential form, we take the base of 2, we raise it to an exponent of 3, and it equals 8. So that's a direct example. Let's begin with our first objective. Change exponential statements to logarithmic statements and logarithmic statements to exponential statements. Let's begin by rewriting the exponential expressions as logarithmic expressions. 7 to the x power equals 15. Well, to write this as a logarithmic expression, we're going to write log, our base is 7, and then we look and see, okay, our exponential equals 15, so that's the number that's inside of our log, and this equals x. Let's do another one. Pi raised to the third power equals m. So the first thing we're going to do is write log. Our base is pi. And our exponential equals m. So that's what's inside of our log. Whoops. And it equals that 3. Okay, our last example, x to the 5th power equals 12. First thing we're going to do is start with log. Our base is x. Now our exponential equals 12, so that's what is inside of our log, and this equals 5. Now, let's go the other way. Let's turn logs back into exponential form. If we have log base 3 of x equals 4, well, in exponential form, we would take our base. So 3 is our base, and our log equals 4. So that's our exponent. X is inside of our log. That's what our whole thing equals. Next, we have log base x of 5 equals 2. Our base is x. Our 5 in our log is what our exponential will equal, and 2 is what the log equals, So that is our exponent. And then we have log base 3 of 8 equals x. Our base is 3. X is what our log equals, so that's our exponent. And our exponential form equals 8. Now, one of the important things about rewriting logs into exponential form is how it makes it easier for us to solve. Take a look at our first one up here. When I give you log base 3 of x equals 4, solve for x, you're probably thinking, oh my goodness, I don't know how to get the x out of there. But if you rewrite it as 3 to the 4th power equals x, now it's much easier for you to find a solution. 3 times 3 times 3 times 3 is going to give us the x. So by rewriting these things into a different form, we are able to solve them in a way that we're more familiar. Let's use our knowledge of rewriting to find the exact value of these logs. So if I want to know what is log base 7 of 49, well, that's like saying log base 7 of 49 is a number. It's something, I want to know what it is. So I'm going to think, okay, 7 raised to some power equals 49. Well, I can figure that out. 7 times 7 is 49. So that missing x is 2. What does that tell me? That tells me that log base 7 of 49 has a value of 2. Okay, what about log base 5 of 1 over 125? What is the value of that one? Well, let's think. 5 raised to a power is 1 over 125. So again, first we rewrite in exponential form. And the first time we were able to solve by rewriting. But this one has an additional step, which I would say use exponential properties. So if you need to, go back and review your exponential properties. We talked about them last lecture. We're going to be using them in this one. They're really important. Please review them if you need to. So now I'm thinking, what power do I need to turn 5 into 1 over 125? The first thing I think is it's going to be a negative exponent because it flipped that 5 to the bottom of the fraction. Now, how does 5 get to 125? 5 times 5 is 25, and 25 times 5 is 125. So that was 3. X is negative 3. What does that tell me? That tells me that log base 5 of 1 over 125 is negative 3. That's its value. Okay, let's do one more. We have natural log of e to the 4th. Now, the first thing you're probably thinking is, what is a natural log? What is this ln? And when we're dealing with, so up here, we had log base 5. And if we go even further, up here, we had log with a base of 7. Well, in general, if you just have a log of a number, log of x, and it doesn't tell you the base, we just assume that it's in base 10. But if we have a log and it has a base of e, remember e from last time? That is a natural log. Because e is our natural number, it's that number that we found that's really great and appears in nature. Makes logs natural logs, and we write natural log as ln. So there's nothing to be afraid of, it's just a log that has a base of e. So we can think of this as log base e of e to the fourth, if we really want to. Now, this tells me e to some power will give me e to the fourth. Well, if my bases are the same and these quantities are equal, that means my exponents have to be the same. X equals 4. And that makes sense because e to the fourth will equal e to the fourth. So this tells me that natural log of e to the fourth has a value of 4. So it's really great, an instant application of why we need to know how to rewrite these things in exponential form and go back and forth, because by rewriting them we can find value. Here is the graph comparing our exponential form to our logarithmic form. As you can see, they are reflected over the line y equals x. This is a graphical representation of the two because they are inverses. And when we see inverses in equations, we see them canceling each other out. Here they are graphically, and they're being reflected over the y equals x. Why is this important? Well, when it comes to the domains and range, when we're dealing with an exponential function, right, a base raised to an exponent, our domain is from negative infinity to positive infinity. We can use any of our x's, and the range goes from 0 up. So if we go back, we can see our red line of the exponential graph. It has that horizontal asymptote, and then it just kind of goes to infinity. Well, once it becomes the logarithmic form, once we use our inverse, you could say, and it becomes that log base a of x. Well, now our domain is from 0 to infinity, and our range is from negative infinity to positive infinity. So what we are seeing happen is the domain of the exponential function becomes the range of our logarithmic function, and the range of our exponential function becomes the domain of the logarithmic function. Graphically, if we take a look at that, we can see, even just in this one piece, I can see my y values, or my range, gets reflected over that axis, and then it becomes the x values, or the domain. So it's really nice to go back and see graphically the explanation. When we go from exponential form to logarithmic form, the domains and ranges are swapping. And that one important aspect is this horizontal asymptote that the exponential form had becomes the vertical asymptote of the logarithmic form. That's really important, and it's going to come up again. Now, Let's use our knowledge of these functions to determine the domain of the logarithmic function. We've got f of x equals the log of 2x minus 1. Well, let's look at our graph really quick. Here we go. If we're looking at the log and we want to know all of the x values that our log function can span, we can see that it's hitting a vertical asymptote right here. Our x values have to be greater than 0. So our log function, anything that's in the log, is going to be greater than 0. That's what we're going to use here. This has to be greater than 0 because our log function hits that vertical asymptote. So 2x minus 1 must be greater than 0. Well, let's just solve for x now. Inverse operation, add 1. We're left with a 2x greater than 1. And if we divide by 2, we're left with our x values must be greater than 1/2. And how do we write that? Well, we will just write our domain, D. We'll put an equals. We'll have an open parenthesis because it's not including 1/2, it's just greater than. So 1/2 to infinity. And that's how we would write it. Our domain goes from 1/2 to positive infinity. Let's do another. Here we have the natural log of x plus 1 over x minus 2. Now this one is a little tricky because now we have a big division happening in here. One thing we know for sure is we cannot have a 0 on the bottom of our fraction. So let's take care of that piece first. We already know that x minus 2 cannot be equal to 0. We just don't want that to happen. So x cannot equal 2. This is important for us. It gives us one piece of what we're looking for. Now we're going to keep looking for the rest of our problem. We know that x plus 1 over x minus 2 needs to be greater than 0, just like before. Now you might be thinking, I really am having a hard time seeing this, and that's totally fine. That it just means you should probably see it. So why don't we see it? The best way for you to understand is for you to see it. Let's type into our calculators the natural log. We'll find our function. We'll find our natural log, there it is. And inside of our natural log on the top, we'll put parentheses around the top, we have x plus 1. All right, it's already getting excited, it's trying to graph it. That's not all, we have more. Divided by, and I'm gonna put parentheses on the bottom too, just to be safe, x minus 2. And close that guy. All right, now we can see what exactly is happening here. This is what happens when we have the natural log of x plus 1 over x minus 2. We can see that we've got a domain and it's split in the middle. We have a gap from -1 all the way to 2 that is not in our domain. But all the other x values are in our domain. So what do? We can write that like negative infinity all the way up to -1. And then from 2 to positive infinity. And in order to bring these two pieces together, we use the union sign. So it's combining these two things. We have from negative infinity up to -1, and also from 2 to positive infinity. And that is our domain for this guy. I highly recommend that if it becomes difficult for you to complete your algebra side of it, refer to your graph. Use your other representations. Graphically, what's happening, and use that information to get the domain that you're looking for. It's not cheating. It's referencing all of your tools. If you know how to graph it in your calculator and you can look at it and understand that you're looking at the domain, all the x values, that is knowledge. Let's continue. Some characteristics of our log function. So, of course, it is represented as log with a base of a of x, and a has to be greater than 1. Here, over here is what our function looks like. You can see that it's the inverse of our exponential. We talked already about our domain going from 0 to infinity, and our range going from negative infinity to positive infinity. In our basic equation, we have an intercept of 1, 0. It's increasing, and it is the reflection of that exponential function. Just to reiterate again, our common log is a log with base 10. We write it as log of x. If the log is using a base of 10, it's customary to just write it as log x. In the same fashion, when a log has a base of e, we just write ln x. And that means natural log. Okay, our fourth objective, graph logarithmic functions. Sketch the graph, and we have 2 graphs here. The first one is f of x equals the log of x plus 3. So how do we graph a logarithmic function? Well, the first thing we do is determine its domain. So what is the domain of the log of x plus 3? Well, the domain is where x plus 3 is greater than 0, so x is greater than -3. This we would write domain is -3 to infinity. Now, nothing else special is happening with this log. It's the basic log function. We've just changed kind of what our domain is. So if we wanted to sketch it, we create our XY graph, and instead of having a horizontal asymptote at 0, it's going to have it at -3, actually. At -3, so it's going to come up. That was a very bad one. from -3 something like that. That would be our sketch. Now we want to sketch f of x equals -3 plus the natural log of x minus 2. First, we need to find what is our domain, and then we need to account for our other transformations. This one is natural log, so the base is e, but it's still a log function, so you're doing fine. First, let's find out our domain is when x minus 2 is greater than 0. And that means that x is greater than 2. Our domain is from 2 to infinity. And the other transformation is that we have moved it down by 3. So to sketch it, we would just take our general log function. We would make sure that our domain doesn't go past that horizontal asymptote of 2, and also that instead of hitting 0, 1, we have moved it down 3. So now it's going to kind of go like that. And you can also double check all of your graphs. After you make your sketch, type it in your graphic calculator and double check it. Make sure that you're on the right track, that you've accounted for everything, and that your sketch looks very, very close to the real thing. All right, our last objective for today, solve logarithmic equations. We are going to use everything that we know and solve. Here we have solve. We're just solving for this missing variable, the natural log of e to the 2x equals 10. Well, first, let's rewrite as an exponential form. So this tells us if natural log of e to the 2x equals 10, remember, if it helps, natural log is the same thing as log base e, and we have e to the 2x equals 10. So we have e to the 10th power equals e to the 2x. Now this has become much easier for us to figure out because our bases are the same and the two quantities are equal, which means our exponents must be equal. So this must mean 10 equals 2x. And if we solve for our x, that gives us 5. Now, the best thing and most important thing that you should be doing is when you solve one, double check it. So let's check our answer. Let's plug the 5 back in. So if we have natural log of e to the 2 times 5 equals 10. Does it work out? So we have natural log of e to the 10th equals 10. And again, you can rewrite this. So we have base of e raised to the 10 equals e to the 10. And that we know is true. Let's do another. This is our last example for today. Log base 4 of x minus 2 equals 2. So let's rewrite. We have a base of 4 raised to the 2 equals x minus 2. Now I'm going to simplify. I know that 4 squared is 16. And now I can solve for that x if I do my inverse operation. X equals 18. Now, like I said before, double check your answer. Log base 4 of 18 minus 2, does it actually equal 2? Well, this means log base 4 of 16 equals 2. And if we rewrite this, we have 4 raised to the 2nd power equals 16. And 16 does in fact equal 16. So that is wonderful. The best thing that you can do when you are solving is to double check. And that's all for today. Again, make sure that you're completing your guided notes with the text to get a complete understanding of this section.